me. So that means I can only really come up with two scenarios here. The first one was disassociating it, breaking it into constituent atoms, piling it all up inside the Pokeball. This satisfies our first condition, that it no longer has a cohesive form to turn into a linear beam of some sort, but it doesn't fit with the whole it would still have mass thing. So the only way I think this could work is if instead of leaving it as mass, we converted it to energy. This would work. It's no longer mass, and it's no longer cohesive. So it sounds like it would work pretty well. So let's see what would happen there. Let's pick some constants just to start off. I started with the Pikachu just because it's so quintessential. According to the Pokedex, Pikachu has a mass of 5.9 kilograms, and I'm going to be working in metric here. For those of you that don't speak metric, kilograms 2.2 pounds. Okay, so Pikachu is about 11, 12 pounds. A raised Pokeball, oh, that one switches too. It starts off this big and then it shrinks on his belt to this big. Okay, I'm not even going to touch that one, but it's somewhere about 2 inches on average. And the volume of a Pokeball, if we're going to say it's a perfect sphere, 4/3 pi r cubed. So we have 5.2 times 10 to the -4th meters cubed. And I think I lost something in there. Yep. Let's convert this to energy using the famous equals mc squared. So we have mass of Pikachu, we can plug that one in, multiply it by the speed of light squared, and Pikachu is worth 1.77 times 10 to the 9th joules. Yeah, what does that mean? Hooray. I give you numbers, they mean nothing. What am I? Network television? Yes, I am assuming perfect efficiency until I make another couple steps, and then you'll see what's going to happen to that efficiency. So we have this energy, and it's going to have to go somewhere. And to show you where it's going to go and what this actually means, what's going to happen is all that energy gets released into the air that's in the Pokeball and the Pokeball itself. So let's see what would just about happen with that. In an average cubic meter of air, you have about 3.4 times 10 to the 25th molecules. This is nitrogen, oxygen, a bit of argon, and all sorts of things like that. So if we kind of divide it out by the volume in a Pokeball, we would get that there are 1.8 times 10 to the 22 molecules of air in a Pokeball. So for those of you that don't speak scientific notation, this is a 1.8 followed by 21 zeros. That's a really big number, but keep in mind that each molecule is really, really small and has a very small mass, which means that it can take a lot of energy and be able to go extremely fast with actually just a very small amount. So let's divide up the amount of energy we just had by the number of molecules in there and see how much average energy we would just have given it. And that's going to be a change in temperature that we get. And the relationship between this is E equals 3 halves kT. So we can plug in the amount of energy. This constant K is 1.38 times 10 to the -23rd. I left off the dimensions just because I was being lazy. And we can solve that for T. So T is going to be T equals 2E divided by 3K, which means our change in temperature is going to be 4.8 times 10 to the 9th Kelvin, which for those of you that don't speak Kelvin is 8.6 billion degrees Fahrenheit. But still, I think this lacks good context, because how often do we deal with billions of degrees? Not often. So let's try to put this in context. What's something that's nice and hot? Blowtorch? 2.3 times 10 to the 3rd. Still several orders of magnitude off. Let's get hotter. Surface of the sun. 5.7 times 10 to the 3rd. Not there yet. Temperature of an atomic bomb. 3 times 10 to the 5th. The core of the sun, where it's hot enough to undergo hydrogen fusion. 1.6 times 10 to the 7th. The temperature necessary to fuse oxygen. 1.5 times 10 to the 9th. The temperature of a supernova. 1 times 10 to the 11th. Where does Pikachu in a Pokeball fit? Absolutely. Now notice what this comes right after. The temperature necessary to fuse oxygen, and what is one of the main constituents of our atmosphere? You capture a Pikachu, you destroy the world. There would be no ash. You would be vaporized. I don't have an animation for this one. It would be very bright though. So since we're on the topic of Pokemon, temperatures of sun, let's talk about another Pokemon here. Everybody's heard of Magcargo? Magcargo? I don't know how to pronounce it. I quit when they were still 150. Magcargo is this weird fire snail thing that lives next to volcanoes. So here's a picture of the guy. According to the Pokedex, his body temperature is approximately 18,000 degrees Fahrenheit. Okay, let's put that back in context with what we just talked about. So let's convert that to Kelvin since I work with those pretty well. And where did this fall? Oh yeah, that's about twice the surface of the sun. Okay, sounds fun to me. So what are the effects of that? Well, the sun does this nasty little thing with ultraviolet radiation, which gives us sunburns if we're lucky, cancer if we're not. So we don't really want a lot of ultraviolet exposure. Fortunately, our atmosphere protects us from a lot of it, because we're looking at the sun through a ton of atmosphere. So the question I want to ask is, if we're not getting that much atmosphere, how much damaging ultraviolet radiation would a Pokemon trainer 10 meters away receive compared to that of the sun? We'll use the amount of sun as a standard reference and talk about just how bad this can get. So to understand this, what we first need to talk about is something known as a black body curve. What a black body curve is, it starts off with this equation up here, which is nasty, and I'm not going to go through. You're welcome. But basically what it says is this. You have the brightness of something being related to its temperature down here and its wavelength. So it will make a curve like this, and the hotter it gets, the brighter it's going to be overall, but also the peak of it is going to be moving more and more towards, if you're in the visible part of the spectrum here, the blue end, and then outside the other end of the blue is the ultraviolet. And you go far enough, and then you get the ultraviolet B rays, which are the ones that are damaging. Over here we have the infrared, which is where humans glow, but Magcargo is going to be a bit warmer. So that's what we're looking at, is how far is Magcargo going to shift this curve, and how much radiation is he going to be getting off in the UV part. So we can use that equation, plug in for the UVB spectrum wavelengths, so 315 nanometers to 280, so that's ultraviolet. And then we can put that in and integrate across that. And for Magcargo, he's going to give off 6.44 times 10 to the 23rd watts per meter squared per steradian, which is a really weird angle that you have to, or unit that you have to use when you're working in three-dimensional spherical trigonometry. Yeah, that's not bad. So basically what it is if you think of a cube and you have a pipe going through it or something, it's linear, but in a spherical coordinate system, it gets bigger as you grow, kind of like if you put a wedge down to the center of the Earth. Same idea, except it's going to be getting bigger as you go out. So Magcargo gives off that number, and then if I do the same thing for the sun only gives off 2.15 times 10 to the 22. So the sun is giving off about 15 times less ultraviolet radiation per square meter than this snail Pokemon. But there's a couple other things that are going to factor in here. First off, the distance. Last year when I was talking about the size of galaxy-sized mechas and things, one of the things I would say is galaxies are big, cars are small. Well, this one, Pokemon are close, sun is far. So that's the summary, is that sun's far away, so it's going to be spreading out that ultraviolet radiation a lot more than this little Pokemon 10 meters away from you. Also, what is important is that the sun has a much, much bigger surface area. Sure, it may be far away, but the sun is freaking huge. So even though per square meter it's going to give off about 12 times less, it has a lot more square meters to give off. So let's try to balance these out and figure out which one is going to win and which one's going to be worse. So for Magcargo, we can multiply